Hello everyone, I'm Preethi Rajendram Soundararajan, ESR1, working in the combustion dynamics team of the EM2C laboratory, which is a part of Central Supelec and CNRS, Université Paris-Saclay in France. Today, we are lucky to be in a world where we can fly to the other corner of the globe in little over a day. This is possible thanks to the innovations in one of the most important components of the aircraft, the engine. My research work is on understanding a phenomenon in these engines called thermoacoustic instabilities. This phenomenon occurs due to the constant dialogue between the combustion and the acoustics of the chamber. Imagine a flame from a gas stove burner that you use every day for cooking or a pile of dry leaves burning. You can hear that it produces some feeble noise. Combustion in general produces sound. Now, if we place an enclosure around the flame, the sound will get reflected back and forth just like in an echo. When the conditions are right and we match the resonance of the chamber, then the reflected sound in turn affects the flame. Here is a video that demonstrates this process. We see a set of cylindrical tubes having the same lengths. Now a small open flame from a gas torch will be placed inside cylindrical confinements and we are going to see what happens. When the flame is placed under different tubes, the tone we hear is quite different. Now when we closely look at what happens to the flame through this transparent tube, we see that the flame is disturbed, resulting in periodic perturbations shedding from its tip. Now imagine an aircraft engine that produces a large amount of power, close to 100 megawatt, in the small volume of the combustion chamber. When such interactions between combustion and acoustics occurs, it can cause undesirable effects on the flame. We can envision the level of damage that occurs due to this event from these pictures. On the left, we see the picture of a new engine. This engine has experienced instabilities and has become the one on the right with utterly damaged engine parts. We definitely don't want these to happen while flying at 35,000 feet in an aircraft. Most of these engines feature an annular geometry. In the picture of the aircraft engine on the left, we can see the shaft connecting the turbine and the compressor in the middle. The engine is located around this shaft. On the right, we see an annular combustor of a gas turbine engine. Since most engines feature annular geometry, with circumferential dimension being greater than the length, these combustors are most prone to azimuthal instabilities, which occur at frequencies where the flames are most sensitive to disturbances. It is thus important to study combustion instabilities directly on an annular configuration. In this way, we are closer to what happens in the reality. At our lab, we study this phenomenon on an annular combustor called mica spray equipped with 16 swirling injectors and operated majorly with liquid fuels. Here is a video showing combustion instability occurring in this lab-scale combustor. We can see that when the instability amplitude is very high, it causes some of the flames to blow off, and this is undesirable. In a one-of-its-kind study on lab-scale combustors, we perform a wide range of experiments by changing the operating parameters such as the fuel and certain other components of this combustor to understand the physics behind this phenomenon. In addition, we also conduct experiments on two complementary test rigs that are simplified versions of the annular combustor. The idea is to establish a dialogue between the different experimental test rigs, for example, to obtain information on the flame response to external acoustic disturbances, and use this knowledge to guide the experiments in the more complex annular system. The large data set obtained from the experiments will help in developing guidelines for designing engines that are less vulnerable to these instabilities. These studies would particularly play a crucial role in the present context of transitioning towards newer, lower carbon fuels and developing engines that are less prone to thermoacoustic instabilities.